We're going to roll right along now with Sean and Chris from Cockroach Labs, strategies to mitigate outages and max uptime. Sean is a senior director of engineering at Cockroach Labs, is an expert in databases and high availability distributed systems, renowned for proficiency in PostgreSQL and CockroachDB. Chris is a senior manager for sales engineering at Cockroach, and he also had that role at Oracle and Cloudera Hortonworks. And so happy to welcome Sean and Chris to our Superstream.
Hey, great to be here. Thanks for the warm intro. All right, so we'll set the stage around resiliency and what this means and how to prepare for it. Especially if you're moving towards the cloud, there are lots of things to think about, right? There are a lot of decoupled pieces of technology that exist in the cloud providers, and any one of them can go wrong. And the old adage of time is money, well, downtime is money as well. And I'm not going to go through all the quotes that are here, but one thing you do have to prepare for once you go to more of a cloud type of architecture is thinking about resiliency, especially at the data tier, at the database level. So if you think about maintenance for databases, this is something that is always in contrast to how to be highly available. How do you do maintenance and always be available? And there's a lot of things that you'd have to prepare for once you set up your data architecture, right? There's ways that you need to think about failover to a secondary database. And a lot of times you have to do that for a lot of different reasons. You could be doing upgrades. You might need to do scaling. You might need to change database settings. You have to build all these operations into your production state architecture to make sure that you can be highly available. The problem with all this is that it requires a lot of work, right? There's DevOps that need to be created. There's humans that need to be involved. There's runbooks that need to be created. And anytime you're going to do async replication from one database to another, there's always a chance of data loss, right? And there's always a chance of having some form of downtime. We've seen this with both traditional SQL databases as well as NoSQL databases. There's just a lot of care that you have to do for just typical maintenance. And with distributed SQL, there's actually new ways to reimagine how this is all that maintenance that you've done in the past and how to prepare for it. There's actually a better way where a lot of this stuff is just automated for you, where the failover and failback are just inherent within the database, where data is reconciled when you do a failover and a failback, where it's a hands-off process and it doesn't require manual intervention to make sure that data is synchronized in both places. Same thing, being able to upgrade without any downtime, being able to change database settings without any downtime, scaling up and scaling down without downtime. These are all things that lend itself really well to be able to kind of let the database manage all those things so you don't have to have human error, you don't have to have extensive runbooks to do these sorts of things. So this is the type of behavior that you'll see within CockroachDB, which we'll go through a little bit more today. Now, on the flip side to just planned maintenance, there's also unplanned downtime, right? These are things that happen in the cloud or even in on-prem architectures where servers go down, disks have problems, there's network outages. And some of the hard failures are well known, right? If we have a server go down, all right, great, we have to fail over to another database server. But there's a lot of intricate gray failures that happen where you do have a disk stall, or you have a network blip, or you have a network partition that only goes one way. That's an async partition. And these are all things that create really difficult things to first diagnose, even understand what's happening, and then understand why, and then how to even fail over from it or recover from it. So once these gray failures happen, it creates a lot of anxiety for operational teams and to think about and how to solve. Fortunately, we've thought about this a lot with Cockroach. If you think about the name CockroachDB, it's hard to kill a cockroach. And so everything that we've built in the database is all geared around resiliency for all types of failures, whether the hard failures or great failures. So, Sean's going to talk a little bit more about this today, of some of the new things that we've brought into the database to help with, some of these really hard or esoteric failures that happen in the cloud. But before we get to Sean, I know everyone wants to hear from him because he's an expert in this area. I'll just explain why this is a benefit for you, right? So historically, we're all used to kind of setting up failover or setting up maintenance and doing all the DevOps for it. We've been doing it for decades, but think about if we didn't have to do all that, right? And if we had to even minimize a lot of that toil and work that needs to be set up initially, it gives you a whole stream of new activities that you can do, right? If you can make availability really easy, then you can be much more productive. And we've seen this with a lot of our customer base where, hey, a lot of the DevOps come off the table, the operations come off the table, and now we can just focus on key things of how we need to help the business, release new features, make sure that we're meeting customer expectations, those types of things. The other piece is that you can also advance your staff, advance the folks that have used SQL technology or NoSQL technology for a long period of time, but help them modernize their own skill set so that you can be more agile within the cloud and use the technologies that have been proven to ride the wave through resilient or high availability issues without any problems. So I'll just leave it with one quote. I'm not going to read the quote, but this was one of my key customers. After I would say about 2.5 years of working together with him, he came up with this quote as to where he saw the value in using distributed SQL technology for all the systems that they were bringing into the Cockroach platform. And they do these events every quarter where they'll do a server outage or they'll do a network outage, and it's all hands on deck for the folks at the bank to make sure that things, the lights are still on. But with Cockroach, it was just nominal. There was no operation that needed to take. It was really the operator team just watch Cockroach go through that particular error or that particular outage and just self-heal through it, automate the things that need to happen without any issue at all. So whereas other teams were all hands trying to figure things out, trying to fail things over, reconcile data and correcting things, again, this was a no-op for Cockroach, which was rather extraordinary. So I'm going to pass this over to my colleague, Sean, who's going to talk to you about some best practices with distributed SQL in AWS, as well as some of the greatest new features that we brought into the resiliency arena around Cockroach.
Speaking of availability, the things that you run into in production are the unexpected failure modes. And in production, we've run into these things where those boundary conditions, like things where you expect to be better than 99% available, you have to go and chase these last little bits of resiliency. And we've been working hard to smooth out those rough spots for customers so that operators and application developers that are effectively beholden to their SLOs don't have to take that into account elsewhere. And that really does help drive efficiency for customers, because you're now able to work on work towards customer deliverables or other initiatives that help with product velocity, so that you as a consumer of Cockroach are able to be relevant in your marketplace, or more relevant in your marketplace. So let's get into it. So there's a lot that goes into providing services for whatever it is that you're doing, and there's typically a handful of tiers. You've got obviously the user, and you've got some kind of a CDN or something caching layer. You load balance into a cloud or into a data center, and you fan out your application and your stateless workload into app servers, and then behind that you have your database tier. And so you've got these big buckets of basically like some kind of a routing CDN layer. You've got a compute layer, and then you have a storage layer there. If your application are load balanced, like why isn't your data? And that's really kind of like one of the fundamental questions to ask when you get into distributed SQL is like, maybe you do want to have your database load balanced, or not load balanced, but even just distributed, so that you can handle and be adaptive to changing workloads. So, as cargo culted infrastructure patterns go, it's pretty common. You've got, some kind of a gateway, you've got a microservice that talks to a caching layer talks to like, a single, traditional database. And then, you're going to have like some events that your microservice is going to write to, and it's going to go on and send something off to a data lake. And every service is going to, stamp this pattern out. It's I'll call it necessary. It's historically been necessary complexity, because distributed SQL is reasonably new, in the sense that like we've only been doing this as a company for 10 years, but it's reasonably new in the sense that there's just not a lot of players doing this kind of thing. And so this is a common pattern, but imagine what happens if you're able to simplify things and you're able to get rid of some of the complexity here so that you don't have to have a caching service. There's time and a place for everything, but if you don't need to have a caching service, and if you're able to have your database produce your events for you, what does that look like? It turns out that things get more simple where you have a microservice, talks to a database produces change events for you, and then you can send it off to some kind of a consumer or analytics or whatever it is. And that's, it simplifies things for your code. You don't have to have an entry point for some kind of a pub sub. You don't have to have something for sending off caching and talking to a caching layer. You don't have to deal with eventual consistency where potentially your cache and your database get out of sync. Instead, you can just talk to the database. And we're going to get a little bit into the fundamentals and a little bit of the architecture of what the database is and why. And then because of the why there, then we're going to talk about some of the features that we've added that really help this story here. So fundamentally, distributed SQL is different. It's not your traditional database where everything goes onto a vertically scaled, Intel or ARM server and you take it to the moon. Instead, Cockroach is a distributed system. It's able to adapt to customer workloads. And so if you've got hot data, Cockroach will split apart data and push data around across different servers in order to scale up for you automatically without any operator involvement. If a node dies in the middle of the day, you don't have to do anything. The system will self-heal and adapt to that kind of a failure mode for you. And so there's a lot of just kind of things and value that are built into the system. So Cockroach Distributed SQL, it's very different. Fundamentally, we're a key value data store. And that's really the most important thing. We have at the key value data store at the bottom and SQL Postgres wire compatible at the top. And everything else in between is kind of implementation detail. Don't have to worry about it too much. But we are going to get into a little bit about how the data gets moved around because this is really important for some of the things that we've done and for what it means to get to those higher availability bits of availability. So as everybody's aware, you've got a Postgres table. You type create table, and this looks, acts, walks, talks, speaks like Postgres. You can take and do a lift and shift if you wanted to. It's wire compatible. Take a Postgres app, point it at Cockroach, just works. Syntax, right? It's looks like Postgres. So in this case, we got a dogs table, and roughly it kind of looks like this, or under the hood, right? And in Postgres, you've got 1 gigabyte extents. We have something similar, and so we take this table and we split it apart into rows and ranges more specifically. So we take this dogs table as our hypothetical example, and we cut it up into 512 megabyte chunks under the hood. And we do that all automatically. The application is totally unaware of this. And we take these 512 megabyte chunks and we're able to, split it across different servers. And so you'll have Carl to Jack will go to node 1 or server 1, and Lady to PD goes to a different server. But we can do this for not just 3 ranges. We're talking literally millions of ranges, which is a huge amount of data to throw at a single cluster. And so we split this data up, we partition, and we handle all of the magic of mapping SQL to these types of ranges under the hood for you. And that's how we distribute stuff. And so distributed SQL. It's in this diagram, it's a little misleading because this shows that range 100 is on node 1. That's not actually true. Instead, what we do is we actually replicate that data. So when I showed that diagram, it's copied. The data is copied 2 more times if you've got replication factor 3, or 4 more times if for replication factor 5. Those are our 2 most common things. And so we've got not only do we have the data distributed, we actually have the data duplicated for resiliency and redundancy purposes, so that if node 1 dies, node 2 and node 3 will be able to pick that up. And so if you've got maybe a cluster of 60 or 150 nodes, that data is going to exist on 3 nodes out of that 150. And we handle this all for you, and we're constantly rebalancing, moving this data around for you, so that you don't have to do anything. But behind the scenes, this is what's happening, and this is an important thing. If I can leave everybody with one thing or one big takeaway, this is the takeaway. We take tables, we split it up into 512 megabyte chunks. The application is totally unaware of this, and we push this around a bunch of servers so that you have a very good, resilient, scale-out database that acts, walks, talks like Postgres. It's Postgres wire compatible. So from an application perspective, this is turns out really convenient. You just talk to an NLB in the case of Amazon. So it looks like a Postgres, it's like kind of like a Postgres super server, right? So you talk to this database, and the NLB will take your TCP connection and it'll fan it out to all of the available nodes, because every node acts as a SQL gateway. And if the node that you're talking to doesn't have the local data, behind the scenes, we'll relay that request to the node that has the data. And we do that all automatically for you behind the scenes. And so there's an extra little, hop there, but like that hop allows you horizontal scale, not vertical scale, but horizontal scale. And so we do that all for you. And as a result, you can just keep adding nodes and, scale horizontally as you need to. You can take nodes down and we'll route around that for you. If a node fails, the data moves around. And the queries keep flowing is kind of the important thing. And, as pushing copies of this data around goes, this is where we get into like some of that resiliency bit. We're actually able to take your data and split it across different AZs in order to ensure that your data is available in different physical failure domains, right? So using US West 2 as an example and using node 1 as an example, we'll see that node 1, node 2, and node 3, they're in different AZs, A, B, and C, right? And so that first range of data, range 100, is replicated into 3 different AZs, and that provides a pretty large, amount of, it's a pretty big, good insurance policy, right? Let's see. So when we do this, right, in order to ensure that you're able to get your data split across, what we do is each node, when it starts up, it has a locality flag where we're able to tell every single Cockroach process that's participating in this cluster which AZ it belongs to, right? So you've got US West, in this case, you have this locality, like hierarchy of locality. So you have US, and you have US West 2 as your region, and then you go to the AZ layer so that we know that we're able to like move the data around it, like using our internal allocator. It moves the data around automatically so that at any one moment in time, there is a copy of the data in all of the different available AZs. And that's this is best practice. Do this when you're in Amazon, when you're in any other cloud provider, but use locality in order to correctly assign the locality to a node, so that nodes, when they're passing around data and making decisions, can distribute things so that you don't have all your data in one AZ. And this is 100% transparent to the application. But as an operator, really important to get right, because if you do this, then you get data resiliency in a way that's just not possible when you're talking to a single point of failure type database, single server, single instance type of a system. But we can do one better. And what we can do is you can actually leverage Amazon placement groups in order to partition out the availability zone. So if you partition count 2, in this case, what you can do then is you can take your availability zone, cut it in half. And so what we'll do is we'll actually split this data across different partition groups within the same availability zone. And there's a little bit of JQ goofiness in here in order to pull this out. But you can see here in this kind of pseudo shell script that we're able to get the partition number. So is this server in 1 or 2? And then Cockroach, in its allocator, will place things intelligently so that it's able to get one copy of the data in US West, 2A, 2B, and 2C. And then if you've got replication factor 5, let's say, it'll actually split the data as evenly as it can between placement group 1 and placement group 2, which means that you don't have 2 copies of your data in the same placement group, like what's depicted here in this diagram. So really important for availability in order to map your data distribution to the physical constraints and fault domains in the real world. And inside of Amazon, a placement group is when using cluster or spread, it's guaranteed to have different PDUs and different rooms and whatever else in order to just physically isolate it. So tip 1, definitely use locality, and where possible, use placement groups in order to partition out the data correctly. So that's really important there. There's a quick question. I'm going to quickly jump to this real quick. Consistency level. Cockroach uses serializable by default. In 24.1, we just added read committed as a consistency level. So we take correctness very, very, very seriously. We're what we call, I call big C consistent. And so it's serializable by default as the transaction isolation mode. And we just added read committed support in 24.1, which came out and was publicly GA'd last week, actually. So that's kind of hot off the presses, but we're very excited about that, being able to add read committed for application. So other things to get to zero downtime. Look, as organizations begin to modernize and move off of single point of failure databases and move to distributed systems, kind of phase one is just moving from a single server to a distributed system. And so like we call that kind of like phase one for a lot of customers in their customer journey. And that involves moving your data and splitting it across. And that provides a huge lift to availability in practice. I personally have moved, 300 something workloads and watched this, just kind of like the availability go from like, 98, 99, 98.5, 99, 3 nines. Like it gets so much better just by moving to a distributed system like this. Lots of complexity that comes with that. Totally worth it, especially if you care about uptime and resiliency. So, and the reason for that is if you're able to move, if you've got a system that is spread across, you care about kind of like this pseudo loosely coupled system, where in the case of Cockroach, you've got all the appropriate failover bits internally. And so it's actually able to act as a loosely coupled system, not a tightly coupled system. And that's really important because, if you have lots of moving parts, as you add more moving parts and it's all synchronously coupled, then you're going to start to find that like your uptime's not great. But with a loosely coupled system, still serializable available isolation. But like if you move to something that's a little bit more loosely coupled, and we're going to talk about one of the things that we did to loosen some of this stuff, all of a sudden your uptime just goes, your high, theoretical uptime gets way better when you start doing the availability math on this. So, if you look at what it is that Cockroach is actually doing, it's sitting there at the top of this dependency hierarchy, where you've got like the physical region of AZ, network, disk. And at the top of that, we're providing a service, a Postgres service, through Cockroach. And so everything else beneath it is basically a critical concern for Cockroach to take care of. And, if a disk goes, has a sad moment, not even like a sad day, but just a sad moment, that can impact your SLOs. And so, it's not necessarily Cockroach's problem, but if we're the one providing the service, it is our problem. So we've done some work to like handle this, because disk IOs typically are synchronous in the sense that like we make a disk, disk write goes all the way down to the disk layer. And then if that disk is sad or has like, it's just a slow disk IO for any reason, then that would show up as a slow write for your application. And so in that regard, we've got some new goodness here, new hotness. So if you deploy Cockroach with multiple stores, right? So in this case, we've got, in 2A there, you see that we've got 2 disks. If one of those 2 disks has a sad moment, just bad latency, bad whatever, that used to be like we would block until that EBS volume came back online. So data that had a leaseholder there, we'd have to like have a little timeout, and that little timeout was potentially impactful for customers. I can say this very comfortably because like we're in production with some really tight, very aggressive SLAs in a lot of places. And like those small timeouts were a big enough deal that we had to go do something about it. So we did something about it. And so new in 24.1, we have this thing called wall failover. And so what happens is whenever a disk write stall happens, that exceeds 100 milliseconds, right? It's not a very big threshold in this case. And it's low enough that it allows for that failover, that write failover to happen without violating a customer application SLA. We will fail over the write to the other disk. And then when that first disk resumes, then we will fail with the wall back over and the write back over so that we're back to kind of like our base steady state. But all write stalls that exceed 100 milliseconds will now be able to handle automatically for you. And this is a really, 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 really big deal when you start chasing those higher levels, like, past the P29, the P39, P49, P59. This is a critical piece. So if you've got an application with an SLO of like, let's say 250 or 300 milliseconds, you can now hit that very reliably on Cockroach, because anything over 100 milliseconds, it'll spill over to the next EBS volume. So really excited about this. Really, really excited about this, actually. I can't stress enough the impact that this has.